We have discussed the Carnot cycle and the reversed Carnot cycle in the previous video, and in this video I'm going to talk to you about the two main functions of a reversed Carnot cycle, which is or the two main cycles that are used in a reversed Carnot cycle, that is the refrigerator and the heat pump. The refrigerator and heat pump. There is very slight differences between these two. The cycle for both these are pretty much the same thing, but the only difference is the area of concentration of these two devices. We will see what are the differences as we go on in this video. Now, a refrigerator is a device that is operating in a cycle. The cycle is a reversed heat engine cycle, and the refrigerator maintains a body at a lower temperature than its surroundings. So a refrigerator is used to maintain the body temperature lower than its surroundings. Now, for that to happen, you need to take some heat. Say, for example, you've got a high temperature body here, say for T1, and you've got an engine or a refrigerator or whatever, and you got a low temperature body here, say T2. Now, if you want to maintain this low temperature from the surroundings, you will need to remove heat. You know, if a body is at a low temperature, say you got a body A here, which is at T2, and its surroundings at T1, whereas T1 greater than T2, then you will always have a heat influx into the body which is at a lower temperature. So you will need to remove the heat that is coming into the body in order to maintain the body at the low temperature T2. So that heat needs to be removed from the body, let's say Q2, and that is to be rejected to T1, the body at the high temperature, let's call it Q1. So that's what is happening in a refrigerator. Now, the refrigerator tried to maintain, say, let's call this body A and this body B. A refrigerator tries to maintain the temperature here, whereas a heat pump tries to maintain the temperature here. So effectively, a heat pump is pumping the heat, whereas a refrigerator, that too is pumping the heat, but that is taking heat, removing heat from a low temperature body and rejecting it to a high temperature body, and the target is to maintain T2, whereas heat pump removes heat from a low temperature body and reject or leave that heat into a high temperature body, and in this case the target is to maintain T1. So heat pump maintains a high temperature, whereas a refrigerator maintains a low temperature. Now let's see the cycle of a refrigerator, how a refrigerator cycle works. It's pretty much the same as our heat engine cycle. You will have let's draw that here. You will have here you will have a condenser, and from the condenser the refrigerating fluid or liquid that passes to the expander or turbine, and that expands here, and that produces a work of expansion. Let's call it expander. And then it moves to an evaporator here, where it absorbs heat from a body at a low temperature, say T2, and from here that goes to a compressor, and from the compressor that goes into the condenser, and in the condenser it rejects the heat Q1 to the body which is at a high temperature T1. The condition is T1 greater than T2. Now we got the expander here and you got the compressor here. It's the same cycle. Flow is like this. Okay, now heat, because it's a compressor, it will take a work input, so you will need to give a compression work here. Now in case of a refrigerator, the concentration is to remove this heat. Heat pump is the same thing, but the concentration is to provide this heat. For a refrigerator, it doesn't matter how much heat you reject here. What matters is how much heat you remove from here. You will need to remove the exact amount of heat that is coming into the body in order to maintain the body at the same temperature. That is the case of refrigerator, and here you will need to input the exact amount of heat that is leaving from the body. Say for example, there are heat losses from this body at T1. Some amount is Q loss, and you will need to provide the total amount, equivalent amount of the heat loss in order to maintain this body at a high temperature. So that is a function of the heat pump, and this is a function of a refrigerator. Both cycles operate in the same fashion and in the same objective. So not the objective, in the same cycle, but the objective is different. Now for a refrigerator and a heat pump, there is a similar term like the efficiency of a heat engine. We call the efficiency of a refrigerator and a heat pump as a coefficient of performance. Or COP, and COP is defined as the desired effect over work input. So in case of a heat engine, you can see this is the desired effect, and for a refrigerator you can see Q2 is the desired effect. So this is the heat you need to remove for a refrigerator, and this is the heat you need to provide for a heat engine. Now let's see how we can calculate the COP for a refrigerator and a heat engine. So for a COP of a refrigerator, you can see Q1, Q2 is the desired effect, and because it's a reversible engine, the work input will be equal to the heat or the heat transfer. Work transfer will be equal to the heat transfer based on the first law. So you can say Q2 is the desired effect, and W1 minus W2 or WC minus WP, not WP, the W expander is the work input. But based on first law, we can say Q1 minus Q2 equal to WC minus WE. Therefore it will become Q2 over Q1 minus Q2, or you can say that is a Q2 over work, Q2 over net work or net heat, both same. And in case of a heat pump, there is only slight difference, that COP of a heat pump, that will be equal to, instead of Q2 you will need to maintain this heat, and therefore this is the desired effect for a heat pump, and therefore the COP of heat pump becomes Q1 over Q1 minus Q2. Again, it's the same work, expander work or compressor work minus expander work, and that's the same thing, Q1 minus Q2, and you can see that is Q1 over W net. You can also write it like that, Now, you can also show that a COP of a heat pump, coefficient of performance of a heat pump, is equal to COP of a refrigerator plus 1. How will you prove that? It's just an easy thing. You just need to understand this. COP of a heat pump is Q1 over Q1 minus Q2, and we say that's a COP refrigerator plus 1. Let's see how it COP of refrigerator is Q2 over Q1 minus Q2 plus 1. That will give you Q2 plus cross multiplying plus Q1 minus Q2 over Q1 minus Q2, and these two will cancel, and you have Q1 over Q1 minus Q2, which is the COP of heat pump. So this term is the COP of a refrigerator. Therefore, a COP of refrigerator plus 1 will give you COP of heat pump. Therefore, COP heat pump is equal to COP refrigerator plus 1. Why is it called a CO, coefficient of performance, and not called efficiency? You will see in problems and in examples that the coefficient of performance can be greater than 1. Efficiency is always the maximum efficiency is 100%, if you know that. So the coefficient of performance can be greater than 1. It's not a condition that COP should always be less than 1 or equal to 1. COPs could go beyond 1. So once again, all the things that we mentioned in the video, there is refrigerator and heat pump both operating in the same cycle. The only difference is refrigerator tries to maintain the low temperature, whereas the heat pump tries to maintain the high temperature or the higher temperature of the two sinks. Now, efficiency of heat pump and the refrigeration cycle is called the coefficient of performance, and that is called desired effect over work input. For a refrigerator, desired effect is the lower heat or the heat rejection from the low temperature body, whereas for the heat pump, the heat input to the high temperature body is the desired effect, and the work input is, because it's an ideal cycle, the work input will be equal to the heat exchange, or work exchange is the heat exchange. So you can say for a refrigerator, COP is Q2 over Q1 minus Q2, and COP of heat pump is Q1 over Q1 minus Q2, whereas your cycle will look like this. It's a T1, let's call it T2, Q2, Q1, T1. Its condition is T1 greater than T2, and you got your compression work and you got your expander work coming out of the system. So that is your cycle. We will discuss further cycles in the next videos. Thank you.